Now, if we want to make up a reaction, we can do it in a series of steps. If we can find a series of reaction steps, we can add those steps up for the overall reaction. So some rules for doing this. So when we're adding two reaction steps together, if something shows up as a reactant in one reaction and a product in the other reaction, they cancel out. If the coefficient in front of them is the same, they'll cancel out completely and will no longer show up. If we reverse a reaction, we are going to change the sign of the enthalpy. So if we take an exothermic reaction, a negative delta H, and we reverse it, this will turn into an endothermic reaction with a positive delta H. Our enthalpies of reaction are given for the reaction as written. So if we multiply the reaction, we also have to multiply the enthalpy. So we can make up the lattice energy by a series of reactions. So the lattice energy is this bottom equation here. The solid ionic compound going to gas phase ions. So to do this, we're going to need the reverse of the enthalpy of formation of that solid phase ionic compound. So the enthalpy of formation for magnesium oxide is taking metallic magnesium reacting with gaseous oxygen to form the magnesium oxide solid. Well, this is putting the magnesium oxide solid as a product. To reverse it around, we'll give it the magnesium oxide as a reactant, which is what we need to match up with the lattice energy. So we're going to reverse the enthalpy of formation. Enthalpy of formation of magnesium oxide is an exothermic reaction, negative delta H. This is can be a combustion reaction. It can be a fast combustion reaction. So when we reverse it, it'll become a positive delta H. So that will give us the conversion of magnesium oxide solid into magnesium metal and gaseous oxygen. So to get toward the gas phase ion, we have to sublimate the solid into gas. So that would be sublimation of the metal from solid to gas. This is going to be an endothermic process. It'll absorb energy. And then once we get that gas phase atom, now we can ionize it, rip off 2 electrons to leave the magnesium ion. This also is going to be an endothermic process. So this is 2 ionization energies combined together. The first and second ionization energy combined together to form the magnesium 2+ ion in the gas phase. We're also going to take the oxygen gas into ionized oxygen. Well, to do that, we first have to break the diatomic molecule into atoms. So we're going to break the bond between the 2 oxygen atoms. So this is the bond energy of oxygen. Once we get our oxygen atoms, now we can add 2 electrons to it to form the negative ion, negative 2 ion. This is electron affinities. It's actually the first and second electron affinities combined. So by using the sublimation of the metal, first and second ionization energies of the metal, bond energy of the oxygen, first and second electron affinities of the oxygen, enthalpy of formation of the ionic compound, we can add those up to get the lattice energy of the ionic compound. When we form ions of our ionic compounds, generally we're going to end up being isoelectronic with a noble gas. That means we'll end up with an electron configuration that matches a noble gas. For nonmetals, we are adding electrons, and we tend to add them up until we get a noble gas configuration. For the metals, we are subtracting electrons. So generally we are removing all the valence electrons and leaving the ion in a noble gas configuration of one electron shell lower than it started off at. Now, not all compounds will form noble gas configuration. Most of the transition metals have two or more ionic charges that are common for it. Some of these may match a noble gas, but most of them don't match a noble gas. Here are a couple common ones also that are not transition metals. So tin and lead, they can lose either 2 or 4 electrons. When they lose 4 electrons, they are almost matching a noble gas. Not quite, because they have a completely filled d level that a noble gas wouldn't have. But they have removed the s and the p electrons. For the +2 charges, they just remove the s electrons. The atoms change size as they acquire charges. When they lose electrons to form a positive ion, to form a cation, the remaining electrons have a larger share of the nuclear charge that is drawing them in, so they get pulled toward the nucleus more strongly, and we end up with a smaller ion. So cations end up being smaller than the neutral atom. Whereas anions, we are adding electrons. Now each electron has a smaller share of the nuclear charge that's attracting them in. So the anion swells in size. So anions are larger than the neutral atoms. And I've mentioned isoelectronic. This is when we have the same number of ions. When we have an isoelectronic series, so a series of ions that have the same charge, the one with the more protons, the smaller the ion. The one with the less protons, the larger the ion. So if we look back here, all these ions have the same number of electrons as neon, so they're all isoelectronic with neon. But the oxygen oxide has the least number of protons in it, so this would be the largest ion. Fluorine will be next, sodium, magnesium, and then finally aluminum. Aluminum has the largest number of protons, so this will have the smallest size. So this is the isoelectronic series. As we increase the number of protons, we're going to be decreasing the size of these ions. Our transition metals have up to 12 electrons. They have the 2 s electrons and then up to 10 d electrons. So most of these transition metals can form multiple ionic charges. They don't form charges up to a plus 12. So they tend to have smaller charges, and then some form charges up to a plus 7 or so. When we ionize the transition metals, we're going to remove the outermost electron first. Outermost electron will be the electron with the highest principal quantum number of n. That means we're going to be losing our s electrons first. This is why most transition metals form a plus 2 ion along with other charges. So we're going to lose our s electrons first, and then we're going to lose our d electrons. And some of the metals, up to column 7, can lose all of the s and the d electrons and end up matching the electron configuration of the noble gas. Some of these highly ionized electrons are very strong oxidizers, meaning they want to take electrons from something else. We also have polyatomic ions. Polyatomic ions are groups of atoms that are covalently bonded together, but they have an overall ionic charge. So they're a combination of covalent bonding along with ionic bonding with a metal.